Yeah. So last time we saw many things about, we saw the definition of basis, and then there were very few equivalent definition of basis, and we also saw that uh, if the size of the if vector space is finitely generated, then any two bases has the same length. Yeah. But so today we will see a proof of the existence, which is sort of existence of a basis in general. So if vector space is not finitely generated, then it requires something called John's lemma, which is equivalent to axiom of choice or transfinite induction and so on. So it's some statement in set theory. Yeah. Because it involves bigger sets. Yeah. So let V be a vector space over a field K, and S be some subset of V, which is linearly independent set. Then um, there exists a basis B of V containing S. Yeah. So that is the statement. So which is same as saying that given any linearly independent set, you can extend it to a basis, right? So that is what so in particular it tells you that so S could be empty as well. Empty set is linearly independent. So in particular it tells you that there exists a basis, or S could be any non-zero element of a vector space. That's also linearly independent. If a singleton non-zero element of a vector space, if it exists, is a linearly independent. So but any linearly independent set, you can extend it to a basis. So I suppose you know what the statement of John's lemma is. Yeah. So what does John's lemma tell us? That if you have a partially ordered set, yeah, so non-empty partially ordered set, such that every chain has an upper bound. So chain means a subset of the partially ordered set, which is totally ordered. Yeah. So any two elements, given any two elements, you can compare them. Either one is less than equal to other, or the other way. Partially ordered means there may not be any comparison between two elements. Yeah? So we will take our partially ordered set to be subsets of V which contains S. So S prime is any subset of V which contains S, and it is linearly independent. Yeah. So S prime also should be linearly independent. So this is a collection of subsets of V. Yeah. And of course it's non-empty because S belongs there. S of course is a subset of V, and it is linearly independent, and it contains S trivially. Yeah, so this set, or this partially ordered set is non-empty, and the partial ordering is via inclusion. Yeah. So now you take any chain in omega. Yeah. So chain in omega means you are taking a collection of subsets in omega, such that any two element has is like given any two element, there is either one is contained in the other, or so on. Yeah. So it's an increasing sequence, if you like. So it need not be a sequence, meaning the indexing set I need not be countable, but increasing collection of subsets. Yeah. So if you take a chain in omega, then each of these SIs are linearly independent. Then if you take the union of these things, these SIs, you get a subset S tilde, which of course contains S, yeah, because each of these SIs in fact contain S. So as long as one of them contains that, then itself it contains S. So S tilde of course contains S, and everything is a subset of V. So this union is also subset of V. So only thing we'll have to check is that S tilde is linearly independent. But that is also clear, yeah, because you take any finitely many elements, finitely many elements in S tilde, then it is contained in some So linear independence means what? Okay, so maybe I'll write some a bit of argument here. So yeah. So to prove linearly independent, what do we have to show? So we see that if there is a linear dependence between certain vectors in V, then it will involve only finitely many elements of S tilde. Yeah. So maybe here I can write. Yeah. So suppose this summation AI Vi equals 0, I equals 1 to n for some n, and Vi is in S tilde. Then these Vi's belong to some SIs, and then you take the maximum of these, the one which is biggest among these SIs, because there is totally ordered. Yeah. So there exists capital N, let's say, such that Vi's belong to S sub capital N for all I. Yeah. So every I Vi belongs there. Yeah. But Sn itself is an element of omega, so Vi's are linearly independent. So Vi's are linearly independent because they are contained in a linearly independent set. Hence, Ai's are 0 for all I. Yeah. So that tells you that S tilde is in omega. Yeah. So we have shown that every chain has a upper bound. Right. So now we can apply John's lemma to say that omega contains a maximal element, which maybe we will call it B. Okay, so this B is a maximal linearly independent set in V by definition, right? It belongs. It is by John's lemma. We have chosen a maximal. It contains a maximal element, so B is a maximal. So maximal element of omega means if you take anything bigger than B, then it does not belong to omega. That means it cannot. So if we add any element in B from the vector space, then it's not linearly independent, right? So it is a maximal linearly independent set. And we already saw that such a set is that by definition, this is a basis. Yeah. There were 4 equivalent definition: maximal linearly independent set, or minimal generating set, or a linearly independent sets which generates V. These were some equivalent conditions for something to be a basis. Or the 4th condition was every element of V can be written uniquely as linear combinations of elements of V. Yeah? So this is a basis. So that completes our proof. Okay. Make sense, everyone?
Yes, sir.
Yeah. Okay. So next, so last time we showed that any 2 bases have the same cardinality if vector space is finitely generated. So the same is true for infinite dimensional vector space as well. So maybe I'll give you a proof for infinite dimensional today. Though we will not use it much in this course, but if you do some functional analysis, etc., you'll handle infinite dimensional vector spaces as well. Hilbert space, Banach space, they are all infinite dimensional vector spaces. So it's good to know that these things are true. Okay. So let V be an infinite dimensional vector space, and let B1 and B2 be 2 bases of so maybe I should have said basis, 2 bases of basis is plural, or yeah, I think basis is plural. Yeah. So so let B1 and B2 be 2 bases of V, then their cardinalities are same. Cardinality of B1 is same as cardinality of B2. Yeah, and of course, to prove this, we can assume that V is both B1 and so B1 and B2 are infinite. Yeah, or let's say B1 is infinite, because if it is finite, then of course we already know what the result that the result is true using that exchangeable trick. Yeah. So let's assume B1 is infinite. Now, if you take a vector V in B1, then of course it's a vector in V, is an element of V. So and V2 is a basis. So you can write it as linear combination of some elements of V2. Yeah. So there exists W1 to WNV, in fact, uniquely as well, but maybe that is not important right now. Such that V, you can write it as some linear combinations of Wi where the coefficient Ai's are in the field K. Yeah. So we are assuming this vector space is over the field K. Yeah. So this set W1 to WNV, we denote it by JV. Okay. Yeah. Is that okay? So now you see for each V in B1, we have got a set JB, which is finite set. Yeah. Now you think about it. So the span of B1 is whole of V. Yeah. So if you think about it, the union of these JV has to be whole of B2. Yeah. Because B2 is a minimal generating set. Yeah. So if it is not whole of B2, suppose it's somewhat smaller than B2, it's of course everything is contained in B2, each of JV. So union is contained in B2, but if suppose you can't cover B2, then a smaller subset, a smaller collection will generate whole of B1, and span of B1 generates V. So that will tell you that this smaller subset generates V. Yeah, which is not possible. So because B2 is a minimal generating set. Okay, so that tells you that this union has to be whole of B2. It can't be any smaller. Yeah. So since so that tells you that this union is whole of B2. So what we have done is you have written B2 as union of some finite sets indexed over B1. Yeah. But then what does that tell us? That the cardinality of B2 is going to be less than equal to the see each JV is finite, so cardinality of B2 is less than equal to the disjoint union of cardinality of JV. Disjoint. So even if you take this disjoint union, so this box union usually denotes disjoint union. Okay, so let me put a dot as well. So if you look at this disjoint union of these things, it is obviously bigger than B2. Yeah. So you can write this inequality. Cardinality of B2 is less than equal to cardinality of this. But each of these JB is finite and B1 is infinite. Remember? Yeah. So then, in fact, B1 cross N has same natural number has same cardinality as B1. Right. So this is some basic set theoretic cardinality axiom. So of course this is way smaller. I mean, or rather, this is. You can find an injective map from this collection, disjoint union of finite sets indexed by B1 to N cross B1, for instance. Yeah. So this has smaller cardinality that, but so this cardinality is same as cardinality of B1. Yeah. So it requires a bit of cardinal arithmetic, but hopefully you know that. So this cardinality is same as cardinality of B1. So anyway, you know that N cross N has same cardinality as N. So it's the same kind of argument. Yeah, so you just have to do this diagonal kind of. So this so that tells you that cardinality of B2 is less equal cardinality of B1. Yeah, but we had not. I mean, B1 and B2 are sort of symmetric. Yeah, so by using the same argument by replacing B1 by B2, you can get that B1 is also less equal B2, and hence they have the same cardinality. So if B2 is less equal B1, B1 is less equal B2, then they have the same cardinality. That's another result in set theory. Yeah. So any questions? Okay, so these are the two things which sort of I mentioned last time, but didn't give you a proof. So now you have a proof of it. Yeah. So now, so remember, dimension is the length of the this cardinality of a basis. Yeah. So, but if it is infinite, we don't really want to worry about different cardinality. So, I mean, now we will assume the vector space is finitely generated, and we will work with finite numbers. So now, if you take a linearly independent set uh, uh, of a finite FD means finite dimensional vector space, then this and suppose that linearly independent set contains dimension of V number of elements, then it is automatically a basis, right? Because that will of course it can't have a bigger linearly independent set, right? Because dimension is same as the size of the basis, and hence cannot have a bigger linear link. And similarly, if you have a generating set which has the same number of elements as the dimension of V, then it is automatically a basis. Yeah. So to cook up a basis of a vector space, you all you have to do is somehow figure out. So somehow, if you know the vector space has some dimension, for instance, your vector space is over the field K is K power n. So as long as you find n linearly independent vectors, you are good. Yeah, then it's automatically a basis. Or if you find a generating set which of size n, then you are automatically you automatically got a basis. Then you don't have to check the other condition. So if you got linearly independent of the right size, then you don't have to check that it generates V. It's automatic. Okay. Okay. So this is maybe, let me make it a little smaller. So is the left panel visible, or should I make it? Is this okay? Is it visible? Yeah. Okay. So I hope this left side is also somewhat visible, so that if you're somewhat behind, then you can look at it. Okay. So we saw many examples of vector spaces. So maybe some of them. So one class of so many of those examples can be, or some of those examples can be explained via more general phenomena. So for instance, if R is a ring and K is some field contained in R as a subring, yeah, then R is a K vector space by, so in fact, R itself has a multiplication overall. So in particular, it has a multiplication by elements of the field K. Yeah. So then you can check that it is a K vector. So all the axioms of vector spaces are satisfied. Yeah, so for instance, Q contained in C, then C, you can also, the field of complex number, you can think of it as a Q vector space. Or Q, so Q square root 2 is a field. Yeah. So if you consider the set consisting of elements of the type A plus B square root 2. So Q square root 2 is basically, so let's just switch off the video. I think it will be better for the recording as well. It will take less space and all. Okay, so this Q square root 2 is basically A plus B square root 2. Yeah, AB rationals. Yeah, so this is actually a field. So I don't know. Do you you must have? I hope you have seen this. Yeah, that this is actually a field, Q square root 2. So C is also a vector space over Q square root 2, and Q square root 2 itself is a vector space over Q. So of course, is C a finite dimensional vector space over Q? Is it a finite dimensional vector space? No, right? Because C has cardinality, is uncountable, right? And Q is countable. So if you have a finite dimensional vector space over Q, it better be countable. Yeah. So C is not so if you take a basis, it's not so easy to construct a basis of C over Q. Meaning, you can't give me a description. Yeah, it uses axiom of choice, etc. So there is no good. So there exists a basis, but if someone asks you to give a basis, it's not so possible. It's not so easy. Yeah, so it's not possible in some sense writing down an explicit basis. So similarly, C is not a finite dimensional vector space over Q square root 2 as well. But Q square root 2 is a finite dimensional vector space over Q. Yeah, what is the dimension of Q square root 2 over Q? What will be the size of the basis? Or what's an example of a basis of Q square root 2 over Q? So for instance, you can take 1 and square root 2, right? So 1 belongs to Q square root 2. So 1, of course, is a linearly independent set over Q because it's non-zero. And square root 2 is again not a rational multiple of 1, right? So square root 2 is again not linearly dependent on 1. Yeah, so that tells you 1 comma square root 2 is a linearly independent set. Yeah, and by definition of Q square root 2, everything is a linear combination of 1 and square root 2. Yeah, so that tells you that this is indeed a generating set as well. Hence, it's a basis. Okay. Similarly, if you take the finite, you have seen finite fields, FP, all of you. So is there anyone who hasn't seen finite fields? You can raise your hand. I can still see you. Okay, so you know what finite fields are, yeah? So FP is a finite field, and there is a finite field of a p square elements or p power n elements for any n, yeah? Um, so this inclusion FP in FP square is again of this kind. So FP square is a vector space over FP, yeah? And one can figure out what the dimension of FP square is over FP. What will be the dimension of FP square over FP? That's an interesting question. What will be the dimension? How many elements does this FP has? So FP has P elements, yeah? And FP square has P square elements. So what will be the dimension of FP square over FP? Can you guess? Anyone wants to guess? Say that again. P. So maybe one should do some calculation. Yeah. So say you look at FP square. Yeah. FP is your field K. Yeah. So you look at K cross K. Yeah. That is a two-dimensional vector space over K, right? K square is a two-dimensional vector. So here K is FP. So how many elements K square will contain if K contains P elements? So for each element of K, so it's a tuple, right? A comma B. So if you fix A, there are P choices, right? And you can vary A in P ways. So there are P square elements, yeah? So that tells you just the two-dimensional vector spaces contains P square elements, yeah? So that tells you FP square has to be two-dimensional, cannot be more than two-dimensional, yeah? It has to. So if you if you add, if you take a p-dimensional vector space over Fp, then it will have p power p elements. Yeah. Or n-dimensional, then it will have p power n dimension. Okay. Similarly, if you take this mn cross n over k, then so m cross n matrices over k, this also forms a vector space over k. What is the dimension of this vector space over k? Mn. So maybe I should write some of these statements. So this has dimension 2. Yeah, this also has dimension 2. This is infinite dimensional. What about the matrices? What is the dimension of m cross n matrix, this vector space m cross? It is a vector space because if you can add any two matrices, and you can multiply a matrix by a scalar and it satisfies all the axioms. Yeah. But what is the dimension of this vector space? Mn. Yeah. So this is Mn dimensional vector space. Yeah. So of dimension m times n. Okay. So now, I guess you know what a subspace is, yeah? So any subset of, so W is a subset of V, which is closed under addition and scalar multiplication, then you call it a subspace, yeah? And if you take a subspace, then it is a vector space on its own right, yeah? So it is a vector space as well. Okay, so we will. For instance, this Q square root 2 is a subspace of C over Q, right? And how about FP cube? So you have, so maybe we can discuss one example. So this depends upon how much finite fields you know. So you know that this is a vector space. And what about FP cube? FP cube is also a vector space over FP. But is FP square a subspace of FP cube? So you know how to construct FP square or from FP? How do you get FP square? No? Oh, okay. So then maybe it is not a fair question. Yeah. So the way to construct FP square is you'll have to adjoin a root of. So there are multiple ways. So you can take the splitting field of x power p square minus 1 if you know what splitting field is, or you have to adjoin a root of a quadratic polynomial over the irreducible quadratic polynomial over Fp, and such a quadratic polynomial exists. Yeah, so that is how you get Fp square, and Fp cube is for degree 3. So it's not true that this is contained in it. Yeah. So what will be contained in it is a power of p square. So Fp power 4 will contain Fp square, but Fp cube does not contain. So F power, so this is not a there is no such containment. So there is no question of such a subspace. Okay. Anyway, so maybe there is some finite field theory, which maybe yeah, so I don't know, maybe for this class it may not be needed, but you can look up. Yeah, so you can try to, so since you're going to do a PhD, it's probably a good idea to learn things on the side as well. Yeah, so learn about some finite fields. Okay. Now let V be a vector space over a field K and W be a subspace. then the dimension of W must be smaller than dimension of B. Yeah. Why is that? How do you prove this?
So we can find a basis for the subspace, right? Because that's a vector space in its own right.
Exactly.
And since the independent set of V can be extended to a basis of V, so dimension of W.
Exactly. So basically, let you start with let B be a basis of W. Then it's of course a subset of V and is linearly independent. Then B is linearly independent and B is contained in V. So there exists B prime containing B, basis of B. Yeah. Hence, dimension W, which is the size of B, is less equal dimension B, which is the size of B prime. Okay. So that proves the dimension of a subspace is less than the dimension of B. Yeah. So let's do something slightly more complicated. So let's say W1 and W2 are two subspace of B. Yeah. Then you can construct this set W1 plus W2, which is basically you take any element of W1 and an element of W2 and add them. So you consider the collection of this set. Then this is of course a subspace. Yeah, because if you take any two such element W1 little W1 plus little W2 and little W1 prime plus little W2 prime, then their sum is also of that form. Yeah. So this W1 plus W2 is this subset of V is contained is closed under addition and of course is closed under scalar multiplication as well. Yeah. So it is indeed a subspace of something went wrong. 1 second. Yeah, became better. Okay. Yeah. So is it? Yeah. So this set W1 plus W2 is indeed a subspace of B. Yeah. Similarly, this W1 intersection W2, that's I mean intersection of two subspace of course is closed under addition and closed under scalar multiplication. Yeah. So it's also a subspace of B. Yeah. So and then there is a formula for their dimension. Yeah. So all this makes sense only if dimension of the biggest space W1 plus W2 is finite. If it is infinite, then also maybe it makes sense, but it's okay. We don't have to worry about it. So left hand side is infinite, and if W1 plus W2 if one of them is both of them are finite, then only all the things will be finite. If any one of them is infinite, then both sides will be infinity. Yeah. So so this formula anyway makes sense only when things are finite. So um, uh, so then this formula holds that the dimension of W1 plus W2 is same as the dimension of W1 plus dimension of W2 minus the dimension of W1 intersection W. So how do you prove this? So it's a similar trick like the previous one. Yeah. So what you do is you start with the basis of the smallest subspace, which is W1 intersection W2, and then try to extend the basis. Yeah. So let's try to do this. So proof. Let V1 to Vn be a basis of W1 intersection W2. Okay, so it's a subspace. Now you can extend it in two ways. Yeah, you can extend it to a basis of W1. You can extend it to a basis of W2. Yeah, so let's give them different names. Yeah, so because it's a linearly independent set in both W1 and W2. Yeah, so let V1 to Vn, and we add some new elements. Let's call them W. Yeah, why not? W1 to Wm be a basis of W1, and V1 to Vn, comma, let's say Y1, yeah, Y1 to YMNL, okay, be a basis of W2. Yeah, so this basis we can extend it both sides and get a basis of W1 and W2. Yeah. Okay. So what is the yeah, but I'll have to get a basis of W1 plus W2. Yeah. Yeah, so now what you do is you check. Yeah. So 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 one has to verify that V1 to Vn, W1 to Wm, Y1 to YL. So the claim is that this is a basis of W1 plus W2. Okay. So if we prove this, then the formula is clear, right? Because left-hand side will be n plus m plus l, and the right-hand side is also n plus m plus l. Yeah. So you only have to check this. But of course, the set we have chosen, it generates W1 and it generates W2, right? So it generates W1 plus W2. That is clear. Yeah. So the only thing we have to check is that it's linearly independent, and then we are good. Yeah. So again, linearly independence is also not bad. Yeah. So you consider some linear combination of these things. Yeah. So let's say summation AI Vi plus so we only have to check that is linearly independent. I should have maybe left a little more space, but maybe this is enough. Bj Wj and plus summation Cj as L I have used. Yeah, I should change the base field to be F rather than K. Yeah, but and yeah, maybe CP for now, but we'll change the base field slowly. Yp P equals 1 to L. So suppose you have such a relation that that this is zero. Yeah. Now So some of it must be so at least one of them must be non-zero. Yeah. So say some AI is non-zero. Yeah. Yeah. So looks like I need some more space. Yeah. So anyway, see this VIs and WMs are all linearly independent. Yeah, because it's a subset of it's a basis of W1. Yeah. So all we have to show is that when we add these YIs, then it still remains linearly independent. Yeah. So there's some of these. So it can't happen that all the CPs are. Yeah. So how do I? Yeah. So if this is zero, then what do you get? You subtract these things. Yeah. So you get that. So I'll move things around. Yeah. So you get that this is. Something gets stuck. Okay, so what I can do is I can write this as equal to minus of this thing. Yeah. Okay. So once I write it this way, that tells you that this element is in. So this and this. Yeah. So this tells you that this belongs to W1 intersection W2. Yeah, because left hand side is in W1 and the right hand side is in W2. Yeah. But VIs are yeah. But the set generated by YIs, yeah, the set generated by YIs so the so this right hand side is an element generated by YIs and it is in W1 intersection W2. So you can write it as a linear combination of VIs. Yeah. So right hand side. You can also write it as a linear combination of right hand side is summation di vi, yeah, equals 1 to n. But YIs are and VIs are linearly independent. Yeah, it's the basis of W2. So that tells you. So this implies. So because so by star, let's say. Star tells you that the CPs and DIs must be zero. So CP equals zero for all P and DIs as well, but maybe that's not important. DIs also equals zero for all I. Yeah. So once CP is zero, then you get that these AIs and BJs must be zero because of this double star. So yeah. So double star implies AI is equals 0 and so does BJs for all ij. Okay. Is this clear? Yeah. So you write this equality, and then the right hand side is in W2, and is in W1 intersection W2, because left hand side is in W1. So W1 so right hand side you can write it as linear combination of VI's, but then you have expressed relation between VI's and YP's, yeah, but they are linearly independent, so all the coefficient must be 0. So that tells you that CP's must be 0, and once you have CP's must be 0, then AI's and BJ's must be 0, because the first set is a basis of W1. Okay, so that proves this identity, yeah. That so this proves that this is indeed a linearly independent set, and we already saw that it generates the whole of W1 and W2. Yeah, so it is a basis, and then the rest arithmetic is straightforward. Is that okay, everyone?
Sir.
Yes.
Sir.
Yeah, tell me. I can hear.
The RHS is a linear combination of YI's, no?
Say that again.
Hello.
Hello.
Sir?
Yeah. Tell me again.
RHS is a linear combination of YI's, but
the RHS is a linear combination of YI's. So how is it in W1 intersection W?
So you look at RHS. RHS is in W2. Yeah.
Yes.
And what about left hand side? VI and WJ. That's in W1. Yeah. Both are same, right? So so left hand side is in W1, but both are same. So it has to be in both W1 and W2. Yeah.
Yes.
Is that okay now?
Yes, sir. Thank you.
Yeah. Any other question? No, it makes sense, everyone? Yeah. Okay. Okay. So this proves this thing. And now, so direct sum of vector spaces, I hope you have seen, but let's fix notation. Let's define it. So if you are given two vector space over a field K, then V1 plus V2 is basically these pairs V1 V2, such that V1 is in first vector space and V2 is little V2 is in the second vector space. Yeah. So as a set, it's this, and then you use component-wise addition and scalar multiplication, component-wise scalar multiplication. So that makes this set V1 plus V2 into a vector space. So this is the direct sum of two vector space. So you can also think of it as product of two vector space. So for finite number of vector spaces, product and direct sum are same, but people think of it as direct sum. They become different only only if you have infinite collection of vector space. So for instance, if Vi is a collection of vector space indexed by a set I, possibly infinite, then to define this direct sum, what you have to do is you have to take an I tuple. Vi is a I tuple, this I tuple of vectors elements in I tuple of elements Vi, where little vi is in capital Vi for each I. And then so if you only do that, then it's not the direct sum. So you also want to insist that most of these VI's must be 0. Yeah. So this VI is 0 for all but finitely many I in I. Yeah. So only finitely many are allowed to be non-zero in this I tuple. The rest is assumed to be 0. Yeah. Then this set is called the direct sum of VI's. Yeah. And again, the addition and scalar multiplication are component wise. So again, this is a vector space. If you take the infinite product, that's also a vector space, but it's called the product of vector spaces, not called the direct sum. Yeah. So if you drop this last condition, it will still be a vector space, but it will not be a product. Okay. So maybe I should say a few more things about so yeah. So maybe I'll say a few things about before I go. So which I didn't write. So for instance, so these things you probably know. So if you have, so we'll worry about only finite many. Yeah. So if you have V1 direct sum, V2 direct sum, Vn some finitely many vector space, then you have maps in two direct you have maps to Vi for each I. This is called the projection map. Yeah. So here the map is V1 to Vn. This n tuple goes to just the ith component of this n tuple. Yeah. So this is the projection map Pi. Okay. But I haven't talked about linear maps yet. Yeah. So anyway, let me define this map, and then this is called the projection map. So we'll see that this is a linear map of vector spaces. Once I define linear map, and there are maps in the other direction as well. So for each I, for all I, we have a map from Vi to V1 to Vn, which sends V2 0 V. So this V is in the ith spot. Yeah, that's the only place it makes sense. Yeah, because Vi is in the ith spot. Yeah. So this is called the inclusion. This is an inclusion linear map. Yeah. So elements of this V1 to Vn are sometimes denoted by V1 plus so this tuple n tuple Vn. This is also sometimes denoted by V1. So Vn. So a priori, this doesn't make sense in. I mean, because V1 may not have anything to do with V2 and so on. Yeah. So the sum doesn't make sense. So you think of the sum in the direct sum. Yeah. So sometimes people use this notation as well if it is a finite collection and stuff. But if there is a confusion, you better use n tuple notation. Yeah. So these are two kinds of maps which you can get from direct sum of vector spaces. And the property of this, so we will see that these are linear maps, and if you do the composition in the right way, then you get, so you first do this map, this inclusion map. This is script I followed by the projection, then you get what is called, then you get the identity map on Vi. Yeah. So you first do this and then the projection, then you get the, if you compose first, if you first put Pi and then this I, then you get a map from this direct sum to itself, but it picks out the ith piece. So that is also somehow called projection map. Yeah. So because it projects onto the Vi component. Yeah. So the image is a subspace of the direct sum isomorphic to Vi. Yeah. So that is also called the projection. So sometimes projections are sometimes endomorphism, linear endomorphisms onto a subspace. So okay. Okay, something went wrong. Let me restart this. 1 second. Yeah, you can see again. Yeah. Is it? Okay, good. And hopefully the left panel is somewhat visible. Yeah. Okay. Okay. So now again, let's talk. So I want to talk more about basis first before I get to linear maps. Yeah. So basically, a basis helps us think of vector space in terms of n tuples and so on. So it gives you coordinates on vector space. Yeah. So let V be a vector space and V be a basis of V. Yeah. Then every V you can write it as A1 V1 up to AN Vn, right? And these AIs are in fact unique. There is no choice involved. There is the vector V determines A1 to AN. Yeah, that is one of the characterizing property of basis. Yeah. So what you can do is identify this V with this column with this vector column vector A1 to AN. Yeah. So I write it. So many people write it as a column vector instead of a row vector. Yeah. So you can identify this this element V of this vector space V with this column vector A1 to AN in some sense. So what we will see once we do this define this linear map, we will see that this any vector space of dimension n is isomorphic to K power n, where K is the base field. Okay. So in some sense, this is an abstract vector space. You don't know how it looks like, but once you give a basis, then it will have coordinates like this. Yeah. So any elements, any element of V, you can write it as linear combinations of Vi, and the coefficients of these Vi's is basically the coordinate of that that element of the vectors. Yeah. So for example, say V is Kn. Yeah. So of course it has one set of bases which is EJs. Yeah, where one is in the jth spot. Right. So this is one basis which is called the standard basis. Yeah. And every element is of course a linear combination of EJ. Yeah. So if you write it as A1 to AN, a vector, a column vector, then it is A1 E1 plus A2 E2 plus AJ EJ. Yeah, that is the standard. But now if you choose some other basis, yeah, so there's no uniqueness of basis, right? So you choose some G1 to Vn, some other elements of Kn. So I'm thinking of Kn as set of column vectors of length n. Yeah. So if you choose V1 to Vn as some other set of column vectors which are linearly independent, then again it is a basis, and again so it will give you new set of coordinates. Yeah. So now for any V in Kn, you can again write it as some AI times Vi for some AIs. Yeah, because this is a basis. So now what is the relation? So how do you sort of relate these coordinates in terms of these bases? So there is a matrix you can form. Yeah. So you consider the matrix C, whose columns are V1 is the first column, V2 is the second column, Vn is the last column. Yeah. Then the coordinates of V with respect to this basis have satisfy this relation. So first of all, C is an n cross n matrix, yeah, because V1 is of length n, is a column of length n, and there are n rows. Yeah. So what happens is C times this this column vector A1 to AN is going to give you a vector. Yeah, it will give you an element of Kn. That element of Kn is precisely V. Okay. So so this is straightforward, right? I mean, if you think about it, we have V is summation is A1 V1 plus A2 V2 plus AN Vn. Yeah. And what does C times A1 to AN means? This matrix multiplication. you look at the first vector times A1 plus the second vector times A2 and so on, right? So if you do the matrix multiplication of C times A1 to AN, you will see that what you get is precisely A1 times the first column plus A2 times the second column plus A3 times this third column and so on. Yeah, so it satisfies this identity. So this identity is, so this particular identity is same as this identity. Okay. So the two identities are same. So in particular, you can recover the coordinates of A1 to AN in terms using the formula that C inverse is V. Yeah, C inverse times V. So if you are given a vector V in Kn, a column vector, and you want to know what are the coordinates of V in terms of this basis B, then you just compute C inverse times V, and you get the coordinates of A1 to AN in terms of so you get this A1 to AN, and this A1 to AN is the coordinates of V with respect to the new basis. Okay. So one has to verify that C is an invertible. So I've just written this down, but next we will check that C is in fact if you take V1 to Vn as a basis of Kn, then C, this matrix you form, is in fact invertible matrix. Yeah. So maybe that we'll do after the coffee break. Okay. So let's take a break, and so maybe I can pause recording.